All right, greeting, welcome to week 6. And this week we will be discussing two questions about root locus. Uh, what is root locus? Root locus essentially helps us answer a question that how do the closed loop poles change when a system parameter is varied. So, previously we have done controllers like PID, PID controllers in various combinations. So there we had terms like Kp, Ki and Kd which are controller parameters. So when we uh, include a controller with the plant and the so formed closed loop transfer function is then obtained, how does the closed loop poles change or vary when we change those controller parameters? That is the essence of uh, root locus. All right, so the root locus provides us with the corresponding graphical visualization, uh, and so let's get right into this question number 1. The open loop transfer function of a unity negative feedback closed loop system is given here as s plus 1 over s square plus 4s. So that means we can write g of s h of s as s plus 1 over s square plus 4s. So the closed loop transfer function is given by g of s over 1 plus g of s h of s. So the denominator, the equation formed by this denominator polynomial is called closed loop characteristic equation. That is 1 plus g of s h of s is equals to 0. So for the closed loop system, we have asked, does the point s equals to minus 1 satisfy the magnitude and angle condition? So let us see what this magnitude and angle conditions are. These magnitude and angle conditions are obtained by uh, this closed loop characteristic equation. So if we just take this minus 1 on this 1 on the other side, we would get characteristic equation as g of s h of s is equals to minus 1. That means this can be divided into two portions. Magnitude of g of s h of s is equals to 1, and the angle g of s h of s is equals to, since this is minus 1, it is plus minus 180 degree, and it's odd multiple, so 2k plus 1, where k is equals to 0, 1, 2 and so on. All right, so let us check whether the magnitude and angle condition is satisfied here by s equals to minus 1. So when we put s equals to minus 1 in g of s h of s, s is minus 1 plus 1 over minus 1 square plus 4 into minus 1. So this comes out to be 0. This implies magnitude of g of s h of s is 0 and the angle is also 0. So this is not equal to 1, which is not equal to any odd multiple of 180 degree. This implies that the point s is equals to minus 1 does not satisfy the magnitude and angle condition. Okay. So now in looking at this second question, we are looking at a open loop transfer function given here. There is a negative feedback and yes, so there is negative feedback, and let's also assume that this is unity feedback. That means h of s is 1. So there are there are 8 different parts to this question. So if we are we'll answer all these 8 parts as we move along and construct the root locus for this open loop transfer function. So we are asking how many branches does the root locus of closed loop poles have and where would they terminate? The complex conjugate open loop poles are located at so the region of real axis that lies on the root locus, the number of asymptotes in the root locus, the angle in degrees made by asymptotes with positive real axis r. So we'll find out those angles. The point of intersection of asymptotes, the breakaway and break-in points, if at all it's applicable, and we'll find out the range of k for which the closed loop system would be stable. So let us slowly get into this. The open loop transfer function is given. That means g of s h of s is equal to k s plus 1 and the denominator it is s cubed plus 2s square plus 2s. So in the step 1 in construction of root locus is locate the open loop poles and open loop zeros. So let's see, poles are roots of the denominator polynomial. So we can take s common. So this breaks into two branches. S is equals to 0 and s square plus 2s plus 2 is equals to 0. So let's solve this polynomial as well. This is s plus 1 whole square plus 1 is equals to 0. This implies the roots are s plus 1 is equals to plus minus j, where j is the complex number. Okay, so where j is under root of minus 1. So the poles are 0, minus 1, plus j, and minus 1 minus j. The open loop zeros are s plus 1 is equals to 0. That means s is equals to minus 1. So let us draw the real axis and the imaginary axis, and let's mark the zeros. So let us mark this length as 1. So one pole is at 0. Let's mark this pole with x. One is at here and another one is here. So these are our three poles: 0, minus 1 plus j, and minus 1 minus j. And let us also mark our 0 at minus 1. So this is zeros, and this would be poles. So the complex conjugate poles are located at minus 1 plus minus j, as we have found out. This divides the real axis into following regions: minus infinity to minus 1, minus 1 to 0, and 0 to infinity. So now we'll look at step 2. Step 2 says we have to locate the parts of the real axis that lie on the root locus. So the real axis has been divided into three parts. Amongst these three parts, we have to figure out which part lies on the root locus. So which are these parts? These are the parts where the number of poles and zeros on the right hand side of the test point are odd. So if this condition is satisfied, then the part lies on the real axis. So let's just draw the real axis one more time. This was -1. So this is the first part, this is the second part, and this is the third part. So if we consider a test point here, say ST1, on the right of it there are the total numbers of poles and 0 are 2, this one and this. So which is 2 poles and zeros on right, which is E1. So this won't come as a part of root, so this will not be part of root locus. If we take a set point here, say ST2, it has one pole on the right, which is odd. So this portion will be part of the root locus. And if we take a test point here, there are 0 poles and zeros on right. This implies this will not be the part. So in the second step, we have located the parts where the real axis, part of the real axis that lies on the root locus. So the region of real axis that lies on the root locus is -1 to 0. Okay. Now let us move on to the next step, that is step 3. Step 3 talks about the asymptotes. Number of asymptotes are given by number of poles minus number of zeros, which is number of poles in our case were 3 and number of zeros were 1. So the total number of asymptotes in this case would be 2. So the number of asymptotes in the root locus plot is 2. Now let us check the angle made by asymptotes. This angle is plus minus 180 degree in bracket 2k plus 1. So odd multiple of 180 degrees divided by n minus m. So where n is number of poles and m is number of zeros. K equals to 0, 1, 2 and so on. So let's take k equals to 0 and n minus m after solving will get plus minus 90 degree. So we know that there are two asymptotes. One will be making The one will be at plus 90 degrees and the other would be at minus 90 degrees. So if we have two asymptotes, where does the asymptote intersect? So we are asking, so part E has now been answered. This is plus and minus 90 degrees. Now we are finding the point of intersection of the asymptotes. This point is given by this expression, sum of the open loop poles minus sum of the open loop zeros divided by number of poles minus number of zeros. So the poles were 0, minus 1 plus j and minus 1 minus j, minus open loop zeros were minus 1, and here we had 3 poles and 1 zeros. So here this would get cancelled. We have minus 2 in the first bracket and minus 1 into minus negative of minus 1 in the other side. So this will become minus 1 over 2. So now let us draw our root locus one more. So we are building our root locus step by step, and now let's put out all the information we have. So we had a, so this is minus 1, this is j, and this is minus j. We had a 0 here, a 0 here, and 1 0 here. We had a pole at 1, and we have found out that the asymptote, let's draw it with blue dotted line, is at minus 1 over 2. Alright, so let us label these points. O as the origin, let's call this as A, let's call this as B, and let's call this as C. Now the step 4 is to determine the breakaway and break-in points. So these breakaway and break-in points occur when we have two consecutive poles or zeros. That means if we have two poles and the root locus starts going towards each other, then at certain point they'll meet and the root locus would go away. Whereas when we have two zeros and it is the root locus is coming from say some direction, then it will break in. So since it is coming in and going towards zeros, this would be the break-in point, and here it will be breakaway points. So since in our case we do not have any consecutive poles or any consecutive zeros on this real axis, we will not have any breakaway or break-in points. So in this case, no breakaway or no sorry and no break-in points. Now let's move on to step 5, and meanwhile let's figure out what answers we have found. So the point of intersection of asymptotes we found at -1/2. The breakaway and break-in points are at, if any, so there are no breakaway and no break-in points. All right. So now returning back to step 5, we have to locate the angle of departure or arrival from an open loop complex pole or from an open loop complex 0. So let us see. Locate the angle of departure or arrival from an open loop complex pole or open loop complex 0. So we are considering the case where k is positive and the angle of departure is given as 180 degree minus the sum of angles made by the vectors from open loop poles to this pole. So angle of departure is defined with respect to the pole. So we pick a complex pole of interest. In our case, these poles are A and B. So if we take pole A, we want to find out the angle from all the other poles. Plus sum of angles made by the vector from the open loop zeros to this pole. So let us replicate, copy this diagram. And paste it here. So let us see, for the angle of departure for this pole A will be 180 degree minus the angle of pole origin at O to A. So let me write it as OA plus the second pole, which is this one, plus angle BA. Plus, now let's look at the sum of angle made by the vector from, let me use green here, this is this. So angle from C to A. So this is plus 90 degree, and this, since this point A is minus 1 plus J, this angle would be 45. So this total angle will be 135 degrees. So angle of departure for A would be 180 degree minus angle from OA, which is 135 degrees, plus 90 degrees plus 90 degrees. So this plus 90 and this minus 90 would get cancelled. An angle of departure for the pole A would become 45 degree. Similarly, now if we say, let's use a marker, if we draw this and if we draw this and if we draw this as well, we have this angle to be minus 90 degrees, this angle to be minus 135 degrees. So this is in essence mirror of the point A. So 180 degree minus angle of OB plus angle of from A to B, and plus we'll have C to B. So let's write all our angles in positive terms, or we can just write it this way. So here this 90 would get cancelled and we'll have 180 plus 135. So 315 degrees. This is also minus 45. So here, since we have 45, here we have its complement. So we have found out the angles of departure. So now we are ready to draw the final root locus. So so first thing is, the region of real axis which lies on the root locus was uh, from 0 to -1. So the lines of root locus start at the pole and end at a 0. So this way. Then we had the root, the asymptote at -12, which is denoted here. Let's write that. And let's make the 45-degree angle, and the minus 45-degree angle. So from here, the root locus would go like this and asymptotically reach this point of -12. Similarly, this side also will see the similar trajectory. Oops. So how many branches do we have? We have total 3 branches. One which goes from 0 to -1 on the real axis, and 2 of them starting from the complex planes A and B, and they will go to uh, -infinity and +infinity with the real value of 1/2. Sorry, -1/2. So how many branches does the root locus have? 3 branches. One terminate at -1, and the 2 terminate asymptotically. Plus infinity and -infinity asymptotically. So given the range, give the range for k for which the closed loop system would be stable. So what is root locus? This root locus is telling us if we vary the parameter k, which is greater than 0, what would happen to the roots. So except the case where k is 0 and we will end up at this point origin, the system would be marginally stable. Everything else in the root locus is in the left half of the complex plane. So the stability would be guaranteed. So as long as k is greater than 0, the system would be stable. So with that, the portion on the problem on root locus is over. In the next week's tutorial also, we have questions coming from root locus again, and we have thought that we would be going ahead and utilizing the next tutorial for MATLAB sessions. So we'll introduce few concepts in MATLAB using some slides, and then we would uh, see how can we work on our topic of control systems with the MATLAB software. So there we'll be learning how to create a transfer function, how do we check its poles, its zeros, and how do we draw this root locus, and so on. And if time permits, we will also take a look at some Simulink modeling, so that we can tune the PID controller in real time, and it would give more of an intuitive understanding of PID tuning rather than the theoretical aspects. Of course, we can do the theory portion as we have done in the last section, where we figured out the controller parameter space. Maybe we'll pick one example from that, and then try to see for ourselves whether we satisfy what we calculated for. So I think that's all for today's session. So we'll meet next time.